Engineering, National Institute of Technology, Durgapur, and Center for Alumni Affairs and International Relations, Student Alumni Interaction Cell of NIT Durgapur, I like to welcome you all in this seminar. We are very much honored to have with us Professor Satyandra Kumar Gupta as a distinguished speaker in this session. It is indeed a proud privilege to introduce Professor Gupta. Dr. Satyandra Kumar Gupta holds a Smith International Professor in the Aerospace and Mechanical Engineering Department and the Director of the Center for Advanced Manufacturing in Viterbi School of Engineering at the University of Southern California. Prior to joining the University of Southern California, he was the professor in the Department of Mechanical Engineering and the Institute for the System Research at the University of Maryland. He was the founder director of the Maryland Robotics Center and the Advanced Manufacturing Laboratory at the University of Maryland. He also served as a program director for the National Robotics Initiative at the National Science Foundation from the September 2012 to September 2014. Prior to joining the University of Maryland, he was a research scientist in the Robotics Institute at Carnegie Mellon University. Dr. Gupta receives his bachelor degree in mechanical engineering from the University of Roorkee, currently it is IIT Roorkee. He received gold medal for securing the first rank in his undergraduate and also gold medal for the best engineering design project during his undergraduate course. He received master degree in production engineering from the IIT Delhi. He received PhD in mechanical engineering from the University of Maryland, and during his PhD study, he was awarded a graduate school fellowship and an Institute for System Research graduate fellowship. He received Institute for System Research George Ralke's Outstanding System Engineering Graduate Student Award in the year 1994. Dr. Gupta's research interest is in the area of physics-wide decision making to facilitate automation, robotics, and robot-assisted 3D printing. He is specifically interested in decision making in the context of the computer-aided design, manufacturing automation, and robotics. He developed decision making approaches that combine heuristic added discrete state space search and the nonlinear optimization to produce high quality decisions by the required decision making deadlines. He is the principal investigator of many prestigious projects in the area of robotics, manufacturing automation, and robot assisted additive manufacturing. Professor Gupta has authored more than 400 articles in ACI journals, conference proceedings, and book chapters. He has also delivered more than 100 invited lectures in seminars and tutorials at the conference and the workshop. He is the fellow of the American Society of Mechanical Engineers, Institute of Electrical and Electronics Engineering, that means IEEE, Society of Manufacturing Engineers, Solid Modeling Association. He serves as an editor for the ASME Journal of Computing and the Information Science and Engineering, editor-in-chief for the Advanced Manufacturing book series by the World Scientific Publishing Company in the year 2016. In the past, he served as an associate editor for the IEEE Transaction on Automation Science and Engineering, ASME Journals of Computing and Information Science in Engineering, ASME Journals of Mechanism and Robotics, and SME Journal of Manufacturing Processes. He has also served as a member of the editorial advisory board for the Assembly Automation and Computer-Aided Design and Application Journal. He has served as a chair of the Design for Manufacturing Technical Committee in the Design Division of ASME. Professor Gupta has received more than 35 awards and honors for his outstanding research contributions. Recently, he has been awarded Design Automation Award from the American Society of Mechanical Engineers and Huge Inspired Research Award from the Viterbi School of Engineering, University of Southern California, and Distinguished and Pioneer Educator Award from the Orange Country Engineering Council. Prior to that, he has received Young Investigator Award from the Office of Naval Research in 2000, a Robert Galvin Outstanding Young Manufacturing Engineer Award from the Society of Mechanical Engineering in the year 2001, a Career Award from the National Science Foundation in 2000, a Presidential Early Career Award for the Scientists and Engineers in 2001, Invention of the Year Award in Physical Science category at the University of Maryland in 2007, Khush-e Toshiba Award from the ASME Design for Manufacturing and the Life Cycle Committee in 2011, an Excellence in Research Award from the ASME Computers and Information in Engineering Division 2013. He has also received 10 Best Paper Award at the conferences and the 2012 Most Cited Paper Award from the prestigious journal Computer Aided Design. Last but not the least, he received Distinguished Alumnus Award from his alma mater, Indian Institute of Technology, Roorkee, in the year 2014. So with this, now I request Professor Gupta to take over the session and enlighten us. Please, sir.
Hello.
Yes, sir.
Hello.
Yes, sir, you are audible now.
I mean, for some reason, it keeps saying that I have been removed from the meeting. So that has happened twice. I'm not quite sure what's going on. Can you see my screen?
Yes, sir. It's visible.
Okay, all right. So should I get started then?
Hi, please start, sir.
Okay, great. So thank you very much for inviting me to present our work. It's truly a pleasure to present and interact with students and faculty at IIT Durgapur. Today, I'm going to be talking about basically how we can improve additive manufacturing through use of advanced robotics. So the focus of my current research is on two different aspects. The first aspect is how can we use robot so that we can realize advanced manufacturing. So we want to be able to use robot to do automated surface finishing, automated composite layup, automated assembly, additive manufacturing, which I'll talk about today. And we also do quite a bit of work how we can leverage advances in new materials, new processes to build the next generation robots. So we have built a wide variety of interesting robots, including a flapping wing air vehicle, robotic fish, robotic hands, robots which basically legless robots which basically locomote by body undulation. So we have done a wide variety of work in building robots as well. So we use robot to improve manufacturing, and we use advanced manufacturing to build the next generation robots. I'll quickly show you some work on our composite processing. So this is a work which is basically showing how we can use robot to process composites.
The system uses advanced computer vision to detect defects and calls humans for assistance. Humans play an important role in robotic cell operations. They provide the cell with high-level strategy to generate good quality plans. Our robotic cell can produce defect-free composite parts. We believe this work will accelerate the adoption of composite materials and lead to the realization of innovative the robotic.
And also, I would like to quickly show basically a video on our flapping wing micro air vehicle. Can someone confirm that you were able to see the video, previous video?
Yes, sir.
Okay, great. So we have been building this flapping wing air vehicle for a while. So the idea is that we want to create this flying platform, which basically will fly by flapping their wings. We have built many generations of this platform. In the third generation, we started integrating flexible solar cells into the wings. And then we will use those solar cells to charge the battery. And then platform will fly using harvested solar energy. And then in fourth generation platform, we added autopilot, which then allows it to basically loiter about a specified waypoint, or you can command it to go to a waypoint. So those were the capabilities we added in the fourth generation platform. And in the fifth generation platform, we added basically thrust boosters at the back of the platform, where we will use two small propellers to boost the thrust, and that will allow vehicle to perform basically very aggressive aerobatics. So then using this, we can dive and also climb very steeply. And this platform flies with a camera, so you can see whatever the platform is seeing. So that kind of gives you overview of different things that happens in my research group. So now coming back to topic for today. So we are interested in exploring additive manufacturing with the robots. So before coming on to that topic, let's kind of review what we would like manufacturing to be able to do. So we want manufacturing to offer features to deliver high performance. So often that means we need geometric complexity, we need material heterogeneity. So manufacturing process should be able to provide it. We want low cost so that products are affordable. We want low lead time. So when the order comes in, by the time the product goes out, the time should be as short as possible. We want to be able to get high degree of personalization. So we want to be able to make custom things. And we want environmental impact of the manufacturing process to be low. So this is kind of our wish list in terms of manufacturing. Now, if we take a look at some common manufacturing processes, so process such as injection molding and die casting deliver low cost through custom tooling. So for any part geometry that you want to build, you will build a dedicated mold or a dedicated die for making the part, and this then allows you to do fast cycle time and low cost. But complexity is moderate, lead time is high because it takes time to build that mold or a die, and this is a mass production process, so you cannot customize, you cannot make 3 different things and yet use the same tool. Second strategy is that you can achieve customization through general purpose tools. So you can do sheet metal bending, you can do machining. In this case, lead time is moderate. Complexity again is moderate. Cycle times are slow because it takes significant time to process or create all the features that you want because you are sequentially processing features, and therefore cost is high. So these are, kind of two different strategies through which traditional manufacturing works. Now, if we compare that to what happens in nature, so on one hand, you have horse, and nature basically, can create incredibly complex geometries. Challenge in the nature is that things tend to grow slowly. And also material choices that nature uses is also limited. If you contrast it, let's say a horse with a motorcycle, you will make individual parts, then you will assemble it together. You can process things fast if you're doing mass production, but again, customization will be limited. So we get contrasting, characteristics, what happens in nature. And nature also does not do assembly. Everything grows in place. While traditional fabrication, there's a lot of assembly involved. You make parts and then you assemble things. So additive manufacturing is a process which we want to grow things in place. Now, in traditional additive manufacturing, there's no part-specific tooling. You can build incredibly complex geometry. The idea is that you're going to take the desired model, you're going to slice it into very, very thin slices, and you will build one slice at a time, or you will add one slice at a time, and that's how you're going to build the entire part. So if you think about additive manufacturing basically is stacking up 2.5-dimensional layers to build the part. So it is basically using kind of two-dimensional or 2.5-dimensional layer to build the part. So it's not really creating 3D layers. In nature, when things grow, we do create, fully three-dimensional shapes there. But additive manufacturing has many benefits. You can realize shapes that are not possible using traditional manufacturing. You can get enormous shape complexity because you're not going to pay penalty for building the tool, or you're not going to sequentially process feature by feature. So therefore, you can have really complex shapes. You can do customization without incurring any cost penalty, and you can eliminate post-fabrication assembly operation. And this view graph shows, very many interesting things that people have built, right? People are now talking about printing dresses. 3D printed hearing aids have been very popular. There are lots of interesting heat exchanger design. People are able to print even 3D assemblies. GE is talking about, basically building all kind of aerospace part. So there's a tremendous excitement about additive manufacturing. But then there are challenges. So if you think about some of the challenges, so let's quickly review them. Since you're trying to build things layer by layer, and these layers are thin, therefore it takes a long time to build a part. And often if you have overhang structure, then you would print a lot of support structure which need to be removed, and then it's going to take a long time. So most additive manufacturing processes have long build time, particularly when you're trying to build large parts. You are approximating the shape via 2D layers, and there is significant potential of delamination between layers. So for many different shapes, if you approximate the geometry by 2D layers, you get very poor mechanical properties. You apply a little bit of force and layers will just delaminate, and that creates major problem. Imagine that if you wanted to print this, micro air vehicle with solar cells in the wings, there's no process which can do that, because solar cells require these exquisite microscale features in order for them to work well functionally. So no current additive manufacturing process will be able to build the mechanical structure and basically create these functional components such as solar cells, particularly the efficient solar cells in the process. So for near foreseeable future, we have to kind of integrate these functional components with the structure which is being created by additive manufacturing. The other limitation is that usually machine will be about 10 times the size of the part that you're trying to print, particularly if you're dealing with metal machines. Now, plastic, of course, machines are not that big, but in metals, machines tend to be very big, roughly 10 times the linear dimension of what you can print, because metal, you have a really complex system for managing the material and also, delivering energy into the material. If you, on the other hand, people say that some of the earliest examples of additive manufacturing are pyramid, which were built layer by layer by humans. So you see, people were able to build things which are 100 times their size scales. So current additive requires huge machine to build large part, and we would like to change it. So these are some of the limitations of additive manufacturing. Now, question is, how can we overcome these? So our vision has been that we want to be able to use robots. Particularly, we would like to use multiple collaborating robots, which can then build large parts. And we want to really use three-dimensional layer. So we want to make 3D printing truly 3D in nature. So we want to do 3D printing with 3D layers. We don't want to do 3D printing with planar layers. We want to build really large part, and we want to basically start exploring new sensing technology for in situ monitoring and control, so that we can actually make sure that if there's any defect forming in the additive manufactured part, we can fix it on the spot. And cell can do material deposition, it can place prefabricated component, it can also do post-processing. So that's kind of our vision, and that's why we believe using robot is truly exciting in this field. So our research has three different layers. The first bottommost layer is additive manufacturing. So where we are interested in basically developing technology which can do additive with non-planar layers. All our execution happens with robots. So we do a lot of advancements in robots. And then since we are using complex three-dimensional layers and we are creating them using multiple different interacting robots, we need advanced artificial intelligence to pull this thing off. Now, if you want to learn more about this entire field of using robots in additive manufacturing, I'll encourage you to read this survey paper, which was published in Additive Manufacturing Journal in January 2020. And the bottom of the slide basically provides reference for that paper. So let's begin basically the very basic technology, printing with conformal layers. So first idea is that rather than stacking 2D layers as done by the traditional AM, and which then creates huge delamination problem, we want to be able to use truly three-dimensional layers. And if we can use truly three-dimensional layers, then mechanical properties are significantly improved, and also we get better surface finish. And we want to do this conformal deposition using a 6 degree of freedom robot. And this in turn then requires us to solve complex trajectory planning and velocity regulation problems. So we have done this and we have created an interesting array of geometries where we have demonstrated that printing time when we use non-planar layers are comparable to printing times when we use planar layers. However, mechanical properties are significantly better, and also in some cases, surface finish is better. This video will just quickly illustrate that process, how it works. So in this case, we are using a prefabricated substrate, and we are performing printing on this prefabricated substrate. And later on in the talk, you will see multi-extrusion system where we can fabricate substrate by the same robot. But the first experiment that I'm showing you is actually using prefabricated substrate. And this type of technology is especially useful when you're printing with composite material. Then you can create really good quality parts. Now, once you are able to do conformal printing, then we can build a setup where we can have multiple different extrusion nozzles. So we have built that setup. So we built a setup where we have 3 extrusion nozzles. So we can do 3 color printing, or you can print support material with one of the nozzles, and you can do printing with others. So we can do quite interesting things in this case. So we have built a setup where we are able to do printing with 3 different nozzles. Once you have capability to basically do conformal printing with multiple different nozzles, then an interesting possibility opens up of multi-resolution printing. So fixed resolution printing means you select a nozzle. If you select a large diameter nozzle, you can print fast, but you get bad surface finish. If you use small diameter nozzle, you print slowly, but you get good surface finish. But if you have multiple nozzle setup, then you could potentially basically print interior of the part with a large diameter nozzle, print it fast, and exterior shapes, you can deposit them with fine diameter nozzle, and that that requires you to use basically conformal printing, because outside of the object is likely to have complex contoured shapes. So we have done that. So our first setup used 2 robots. So we have 2 collaborating robots, and using that, we showed that we can actually build parts which are much, much faster than the smaller diameter nozzle. On the other hand, the surface finish was as good as the smaller, part which built as fast as basically the higher diameter nozzle, and surface finish as good as the smaller diameter nozzle. So we were able to find the right balance between the 2. And at the bottom of each slide, I have included the papers which basically provides more detail. So this work was published in IEEE International Conference on Robotics and Automation. And after that, we have built a 1 robot setup where a single robot with 2 extrusion nozzle is able to accomplish the same result, because again, we don't want to tie up 2 robots doing this printing. So again, we demonstrated that using a single robot setup, we can actually achieve similar results. And this paper is going to be appearing early next year in ASME Journal of Computing and Information Science. As I mentioned before, a lot of additive processes require use of support structure, which slows down the process quite a bit. You have to remove the support structure, which is wasting of material. It might also lead to poor surface finish. Overall, it increases the time. So whenever possible, we want to avoid support structure. So we built a setup where we are using 2 collaborating robots. So bottom robot is holding the build platform. Top robot is doing the deposition. And in this case, when we start printing parts which are leading to overhang, then we start tilting the base platform, and therefore we can compensate for gravity, and therefore we don't require use of support structure. So this type of technology then gets rid of support structure.
Hello, Professor Gupta. Hello. Hello. Professor Gupta, you are in muted condition. Please unmute yourself.
Okay, can you hear me okay now?
Now it is okay, sir.
Yeah, I don't know. I was not even touching the screen, so I'm not quite sure how I muted myself. So where did you lose me? Hello?
So it's okay now, sir.
Okay, all right, so I'll just continue. So we can dramatically reduce basically printing time, as you can see. Sometimes, for this large part, with support structure, it would have taken us 11 hours, 42 minutes to print. We can print it in 1 hour and 13 minutes. And this work was published in Additive Manufacturing Journal in March 2020. Another interesting thing that we have done is that rather than doing extrusion-based printing, which is a basically point-based process, we also build a process where we can stack sheets, we can cut sheets, we can shape them and stack them. And that allows us to actually, additively manufacture a whole variety of interesting things, including wings of flapping wing air vehicles, as well as wide variety of other interesting structures as well. And this paper was published in Additive Manufacturing Journal in 2019. Another interesting thing that we have demonstrated is that you can, during printing, using two collaborating robots, you can embed externally fabricated components. So in this case, we have demonstrated that you can integrate assembly and additive manufacturing. So we are able to generate plans for picking up components and then insert them. And then once a component has been placed, then we can print around it. So that allows us to create, wide variety of interesting, type of products where we can embed externally fabricated components. My file was huge, so I have split that into two files. So I'm going to stop sharing, pull up the next file, and then I will share that second file. So just give me 1 minute to make that change in the file. Are you able to see my screen?
Yes, sir. Yes, sir.
Okay, great. So our recent work has been conformal wire arc additive manufacturing. So here we are basically using robots to do conformal printing using VAM process. So we can print interesting shapes using this process. And we have demonstrated, basically that that we can actually get reasonably good material, properties. So we can do interesting shapes and we can get reasonably good material properties. So to just quickly summarize, robot by using conformal printing can improve mechanical properties by again being able to print out of plane. You can tilt the part when you're printing it, and then you can reduce the build time due to support less deposition, and also you can do multi-resolution printing. Once you can do conformal printing, then you can also do multi-resolution printing. We can insert prefabricated component during the assembly process, during the 3D printing process, and therefore we can integrate assembly and additive manufacturing. And we enable many more material choices in multi-material printing, again, by mixing the material which is being printed using either a two-robot system or a multi-nozzle system. We offer lots of interesting choices. So all these benefits, basically illustrate that the idea of doing additive manufacturing with robots is a promising idea, and it holds a lot of promise in terms of eliminating many of the known limitations of the current additive manufacturing process. So then the question comes in, okay, so what are the deep research issues? What are some of the fundamental problems that need to be solved? So additive manufacturing process, when you do 3-axis printing, where you're using Z-axis only just to, increase the layer height, or you go from one layer to the other, you're largely operating in 2D. So planning problem is simple. Control problem is very simple. Identifying parameters is very simple. The moment you start using these complex 3-dimensional layers and you start creating these 3-dimensional layers using 6 degrees of freedom motion, sometimes 12 degrees of freedom motion, then you are solving really complex planning problems. So your computational problems are really, really tough now. And that's what I'm going to walk you through and illustrate what some of the interesting work needs to be done in these fields and what we have done. So the reason why this problem is so hard, that robots are highly coupled systems. Even if you're drawing a line along x-axis defined in the robot base, but all 6 joints have to be moving in a coordinated way in order for you to do that, if you are trying to maintain certain orientation. So robots are highly coupled systems. There's no, just using a single motor to get something done. Robot performance is also highly non-uniform over the workspace. You can get very good accuracy at certain places, certain other places you will not. Workplace may have singularity. So all kind of challenges that you're going to have because of this non-uniform performance. And robots basically are highly nonlinear systems. So this high degree of nonlinearity makes many of these problems quite challenging. And as we start integrating external sensing and coordinated motion between multiple different robots are really, really complex systems. So all this makes these computational problems very challenging. The first problem that we want to study is path constraint trajectories. So the idea is that you know how your tool tip needs to move in order to create the geometry, and you know how the part should be tilted. So that path constraint is given to you. Now you have to figure it out how the robot should move, how robot joint should move so that the tool moves with respect to the intended object the way you wanted it to move. There are constraints for the path. You want to avoid collisions between the tool and the already fabricated part. You have manipulator joint limits. You have manipulator singularity. Those are all kind of manipulator constraints that you have to also meet. So you can pose this problem as a problem of trying to find basically a joint space trajectory for the robot where you meet all the constraints, and you can basically have an optimization function which could be minimization of time, or it could be minimization of basically some other performance variable which could be effort that robot is taking to get this thing done. Now you can pose this as a nonlinear optimization problem. However, existing nonlinear optimization approaches will not be able to solve it because your constraints are highly conflicting. And once you start using nonlinear optimization, you'll get stuck in local minima, and those local minima basically would not even be a feasible solution. So our idea in this space has been to use an adaptive representation of configuration variable. So we will keep adding more variables or providing finer resolution where a lot of changes have to happen, and we use relatively simple representation where things are not going to change that much. And then we want to use basically successive refinement strategy for solving this problem, because giving the problem all the constraint in one go simply will make this problem impossible to solve. So the way we work is that we create a optimization problem instance, we create initially some approximate solution. Using that, we learn where we need more resolution in terms of, so we're solving this problem with the spline. So we're basically asking question where you need more control points and where you can get away with fewer control points. And then we want to apply constraints successively. So we don't want to be throwing all constraint at once, because if you throw all constraint at once, unfortunately, problem is not going to be solved. So in this case, we want to start with some basic constraint, then add few more, then add few more. So that's a successive refinement idea. And we have demonstrated. Hello. So we have demonstrated that basically we can solve really complex path constrained trajectory planning problem with this idea about adaptive representation and successive refinement. And this work was published earlier this year in International Journal of Robotics Research. So you can get more detail from that paper. The other interesting thing that needs to happen is basically you need to learn process parameters. So for example, when you're doing VAM process, there are a number of parameters that you need to learn. So you need to learn tool velocity, tool inclination, tool distance, feed speed. So these different things you need to learn. Now, one thing that we know is a lot of challenges that when you're making these sharp angles, then you start creating bulge. So can we learn this so that robot then can regulate its speed? The approach for learning this is basically inspired by active learning. So the idea is that you do some initial experiment, you fit a surrogate model, and then you start selecting process parameters which will try to find the right balance between exploration and exploitation, and then you will perform the task and update the model, and then hopefully your performance will improve in few trials. So in this case, we begin with a fixed velocity scheme, then we do some experiment where we try regulating velocity around the corner, then we scan the part, we build the model, and then we reduce the dimension of those observations in terms of curvature and heights. And then we run anomaly detection approaches to that to determine, which particular runs seem to be showing anomalies, and using that, then we try to figure it out how the velocity should be regulated. And then we can learn that, and then using velocity regulation, then we are able to demonstrate that we can get the. And this work appeared a couple of months ago in the ASME Computers and Information Engineering. So if you have a large robot and you're trying to print a part in it, different regions of the workspace will give you different accuracy. So accuracy changes quite a bit depending upon the region of the workspace. Some regions of the workspace, you'll get very good accuracy. Some regions of the workspace, you're going to get very bad accuracy. And that's known, thing, because robot, again, because of the way joint angle mapping happens to accuracy, accuracy over the workspace is highly non-uniform. So we are interested in solving the problem. Then when we're trying to print a small part, then where should we place in the robot workspace so that we get the best print quality? So we begin with basically modeling what the effect of the joint error is. And so we catalog and model different kind of joint errors as a function of configuration of the robot. And then using that, then we can look at part placement optimization, which then basically we try to see where the different kind of trajectories will be needed and how can we basically place the part so that we meet the reachability, collision, build direction, path consistency, all different constraints, and yet we maximize the achievable accuracy. Using that type of formulation, we have demonstrated that you can actually find the locations where you can get really good accuracy and you can get much better print. And this work was published earlier this year in IEEE International Conference on Robotics and Automation. And we have demonstrated that if you're printing certain kind of geometries, what are the ideal location for printing them, and compared to wherever a human might have initially placed and what kind of improvement in accuracy can be achieved. Now, articulated robots have high degree of repeatability but poor accuracy. So accuracy can be 10 to 20 times compared to repeatability. For example, repeatability could be 20 micron, accuracy could be 400 microns. And the reason for that is that when a robot arrives from factory and it has been calibrated at factory, its parameters might have drifted, or the factory calibration might not have been very accurate, or they might have made certain simplifying assumptions. So all this causes challenges. So when you start doing printing with robots, then you will not get very good quality results. Now, if you want to do additive manufacturing with robots, then you have to address this accuracy problem, because without that, you're not going to do good quality printing. So the idea in this case is that can we build a compensation scheme so that when we are going to be performing printing, we will compensate the trajectory so that its execution performance improves. And you will apply this on top of the existing robot controller. So the idea is that you have input trajectory, you can sample it, and you can take a very small sample of it, you can execute in the robot, see what kind of error you're getting. Then, based upon that error, you can train a neural network which can apply compensation. And then this neural network, then you can apply on the entire trajectory, and you can actually then go ahead and do the printing. So we have solved two different versions of this problem. The first version of the problem we solved was where we built a compensation scheme in the workspace. So in this case, basically, we are interested in knowing which regions of the workspace we were printing and what were the locations and angles. So we basically compensated in angle space, position space, and as well as the time space, because robots often are a little bit sluggish because they're overdamped. So we compensate in all those 3 dimensions. And using this, we have demonstrated that just using 4 to 8% of sampling by training a neural network, we can actually produce really good results. So we can actually reduce the error significantly. We demonstrated this by basically trying to draw a circle on a moving platform. So in that case, we begin by drawing a reference trajectory, which is not a circle, but the idea was in a moving platform, this will turn into circle. So when we ran uncompensated trajectory, it did not work out. But when we compensated the trajectory, that we did get very good results. And this video illustrates that. So this is uncompensated, where you are unable to get good results. And this is now a compensated trajectory where we will be able to create a good circle on a moving platform. So platform is moving, robot stationary. We have also solved the same problem using configuration space neural network. So in this case, rather than performing compensation in the workspace of the robot, we are directly working in the joint space, and we are basically solving the problem in the joint space. So in our MSec paper this year, which also received second place best paper award at the conference, we demonstrated that using configuration space compensated trajectory, we are able to achieve very good performance basically. So again, small fraction of trajectory, we use it for training, then be able to execute it really, really well. So far I have discussed how we can generate trajectories, how we can identify process parameters for doing printing, how we can find the right place to place the artifact in the robot workspace, how we can compensate the trajectory, but some problem will require multiple robots to print concurrently. So in our recent work, we have been looking into a 3-robot cell for printing large metal parts. So the motivation behind this work is that traditional powder bed AM process deposit material at a few 100 grams an hour. A single robot VAM can do 10 kilograms per hour, but if you have 3 robot VAM, then you can do 30 kilograms per hour. So to build big parts, we will need this multiple collaborating robot of performing printing. So now the problem is that if we have n manipulators, we want to place the robot such that the work is distributed equally among the robots. No robot is idle. Part is within the reach, or the section of the part which a robot needs to print is within the reach of the robot. And we minimize the inverse kinematic inconsistencies in the robot path. And I'll explain that idea in a few minutes. So we begin by decomposing the part. We search for planes which partition the part such that we can have equal distribution of the work among the robots. And then we start searching for robot placement so that robot can perform the task which is assigned to a particular robot. So here is a complex, geometry which is being printed. In this case, we found out what the ideal distribution of the robot should be to print it. Now, in industry, people have talked about just building, a cell where each robot, angle-wise, you just distribute them 120 degrees apart. So we have demonstrated that if you use that cell configuration, you would struggle with this part. Your IK inconsistencies are going to be quite high. On the other hand, if you can basically optimize the placement of the robot, you can reduce the IK inconsistency. Now, anytime you have IK inconsistency, there's a potential that you will cause a defect in the part. So that's why you want to minimize that. Here's another example of a part where again, we need to distribute the load among the three robots. And again, preferred configuration in this case is not a configuration where each robots are, 120 degrees apart. They are at different place. And in this case, we are able to basically solve the problem with zero IK inconsistencies. So here's an example of a third part. Again, in this case, we are able to solve the problem with zero IK inconsistencies. Here's a video that will illustrate actually IK inconsistency as well. So this is showing basically where at a point robot hit its joint limits and it has to find a solution from a different IK family in order for it to proceed. And that means that arc had to be shut and again start again. So every time that happens, then there's a potential for creating a defect. So this is just showing now when you optimize robot placement and divide the work basically in a balanced way, then you can get significantly better solutions. Okay, so let me conclude my presentation. So building additive manufacturing cell using robot removes constraint associated with traditional 3D printing. You can do conformal layers. You can do multi-material fabrication. You can do supportless fabrication. You can insert prefabricated component during additive manufacturing. And you can start integrating inspection, prognostics, and health management tools into your robotic cell, which will then ensure that you are creating defect-free parts. I would like to acknowledge all my students who have contributed to this research. I'd like to acknowledge all our sponsors who have funded this research and all our industry collaborators who have given us the equipment and a lot of expertise and advice which has enabled all this work. So with that, I will conclude and happy to answer any questions.
Okay, thank you so much, sir, for your inspiring speech. Now, house is open for the question for the participant. I request one of the student volunteer should coordinate the question answer session, please.
Good evening, sir. Our first question in the question answer session is what are the skills and softwares that are required to make career in robotics?
So, I mean, the large number of, software. So software is something, basically which changes from depending upon which industry segment you're looking at it. Skills wise, you need to, really understand nowadays in the modern world of robotics, you need to understand robot dynamics and controls. You need to understand planning. You need to understand some perception, some computer vision. Machine learning has become very important. So these are all, different skills that you need to build. And then depending upon which segment of industry you work in, different software will be important.
Hello, sir. Am I audible?
Yes.
Sir, myself, Dr Gupta. I graduated this year in mechanical engineering from NIT Durgapur. I worked a bit on robotic WAM under the guidance of Professor Roy. Sir, just wanted to know, is that technique of conformal layers that you demonstrated is applicable in the field of robotic WAM also? Means, can we print conformal layer using robotic WAM technology? And if
Yeah.
yes, will that sharp corner problem be magnified that you demonstrated in case of WAM?
So, I mean, we have done conformal printing. I showed some slides on conformal printing or a video on conformal printing. So conformal printing certainly can be done with WAM. Now, depending upon the geometry, sharp, angle change. I mean, basically the idea there is that if nozzle is going around a corner and spending too much time there, that is doing double printing and depositing too much material. So you have to speed it up, right? So depending upon the geometry, problem may get magnified or may not get magnified. It all depends on the geometry.
Okay, sir. And secondly, sir, actually, I'm extremely interested in the field of robotics, actually. I've studied a bit of that. So what's further opportunities for collaborating with you or pursuing some higher study if possible under your guidance? If you could tell me.
So, that question, I think we can just discuss it over the email, right? So you can look at a different kind of work which is going on in my lab.
Yeah, surely, sir. I would love to look at your papers.
Yeah.
Okay, sir. Then I'll contact you via email then.
Sure.
Yeah, thank you so much.
Mm-hmm.
The next question in our panel is how does 3D printing become more effective in the medical sector and which type of materials are required?
So medical sector is again very vast sector, right? And different components of that sector would need different type of technology. I mean, 3D printing seems to be doing quite well right now in the space of, basically, cosmetic dentistry. It's doing well in hearing aids. It's doing well in certain other kind of, braces and support structure that people are producing. People are talking about implants, so that's where also work is happening. People are talking about now printing, basically pills using 3D printing. So there's a lot of exciting work happening there. People are talking about bioprinting, which they want to print organs. So many different sectors, each of them have different sets of challenges. Some of them are material challenges. Some of them, basically are processing challenges. So challenges are quite different depending upon which sector that you're looking at.
Okay, sir. The next question is the arena of electrodynamic inkjet printing has picked up at a rapid pace in recent years. What are the chances that we see full-fledged automation in the field of manufacturing in near future?
So, I think the significant progress will be made in automating manufacturing, but near foreseeable future, no single process can actually do everything that you want. I mean, you will need different material, you will need features in different size scale, and therefore inherently in the end, you need to have some sort of assembly and integration. So therefore, full automation is not going to happen anytime soon. And there's no need for it to basically for that to happen either. We just want to boost human productivity at a level where humans are not doing basically jobs that people don't want to do or which compromises human health basically. We will make significant amount of progress, but no single process is going to do everything for you, and therefore you will use multiple different processes, and then you have to do integration in the end.
So our next question is, which part of the robot-assisted 3D printing has greater opportunities in future research? Are algorithms and codes to be developed, or the mechanism and motion and mechanical engineering areas are to be discovered more?
So right now, more potential is on the algorithmic end of it, because different processes require, the defect form in a different way. Processing need to happen in a different way. So there's still a lot of algorithmic advances which are needed to make these things more robust. Now, robots are also being talked about now in powder bed. How do you clean the part? How do you post-process the part? How do you calibrate the machine? So there are a whole bunch of opportunities which are gonna open up, which will, try to reduce the manual labor, not on the processing end of it, but also the post-processing, aspect of the process, as well as things which are related to machine operation. And large number of opportunities which are in the software and algorithmic aspect are going to be many more. Obviously, there are opportunities in the hardware as well.
Okay, sir. If any participants have any question, please go ahead. Anyone with any questions, you may ask. Yes, sir. There is one question. What are the limitations and trending issues with 3D printing?
What are the limitations and
trending issues with 3D printing?
So, I mean, the 4 things that I discussed in the beginning of the talk, I mean, currently 3D printing is a slow process. So it's great if you are making things which are 1 centimeter by 1 centimeter. Yeah, sure. In that case, you can print it in an hour. But if you're making things which are meter scale, process is too slow. If you are trying to make things which will be large but require micron scale features, then you have to do assembly and 3D printing concurrently. So that's another big issue. How do you integrate externally fabricated functional component into 3D printing. Then there are challenges. How do we make sure that we can deliver really good mechanical properties? And that becomes supremely important when we are dealing with, composites or certain type of metal. So that becomes extremely important. So yeah, so create good quality part, make them accurate, deliver the right mechanical performance, make them fast, integrate externally fabricated components. So these are all challenges that need to be addressed, and people are making progress every day. And there's a tremendous interest also in hybrid manufacturing, where people want to do some part of it using additive, but then they want to do some part of it using subtractive. So all kind of opportunities.
Oh, okay, sir. Sir, the next question is how much a fully automated product using robot can be sustainable and trusted by people who are gonna need it?
What's the last part of the question?
Uh, so I'm repeating the question. How much a fully automated product using robot can be sustainable and trusted by the people who will be getting it? Means
So
using it.
yeah, I mean, sustainability is, processing dependent, right? So, I mean, ultimately, whether robot make it or people make it, I don't think there is going to be any dramatic difference in the main sustainability drivers, which are processing level energy consumption and the type of material which are being used. Yes, robot will use some energy to make the part, but that's not, significant amount compared to what processing energy is. If that was the question about sustainability end of it. Now, trustworthiness of robot, produced product will be significantly higher, because once you start integrating in situ sensing and monitoring, then when the product is finished, you would have, complete history of how the process was actually, what kind of forces were seen by the part, what temperature, what pressure. So you will have a complete process history. And therefore, in the end, you will be able to create much better quality product than what you can do by manual labor. So in terms of traceability, what happened during the process, I think robots do a lot better job than humans do. So that's kind of how I look at things. Now,
Okay,
the sustainability question is more in terms of, what will human do when robots are doing fabrication? What jobs humans are going to do? That's a different type of flavor to it. And of course, for that also, a lot of jobs in agriculture shifted to manufacturing. But similarly, if more robots get used in manufacturing, there will be opportunities for human to do more creative work in the manufacturing, more personalization, more customization. So there'll be tremendous opportunity. I mean, the world would look very different if we start using more and more robots.
Okay, sir. So now there is a contradictory question to this current technology. Means if there any effect of human life or employment due to increase of this robotic sector?
So absolutely. So, basically fewer humans will be used in, will be needed in manufacturing. So that's what I was saying before. So idea would be that, increasingly human will have to be involved in more creative aspect of the work. I mean, we are basically saying that physical labor needs to be done by the robot, but remember, product can have many facets to it, and value can be created by human in other aspect of the product than simply doing the physical labor. So as I said, once more robots start being used in manufacturing, then there will be potential for human to do something different and better. And that future, we quite don't know yet, right? So once this starts happening, we'll see where that happens. But we have seen this many times before. So, I mean, there's no reason for us to believe that this is not going to be the same this time.
Okay, sir. Sir, can you please tell us the possibility and opportunities of higher studies at US in the area of additive manufacturing and robotics? It will be helpful for many students.
So, I mean, both additive manufacturing and robotics are very popular research topics. I mean, most good universities have professors working in that area. And, most of them are interested in every year getting new students. So I think there's tremendous opportunities in both of these spaces.
Okay, sir. So in the last, I would ask that based on the current scenario, what is one advice you want to give to all students?
I mean, advice for every student, I give the same advice that, find what your passion is, right? Because in the end, you have to find what makes you happy, where you can excel, where you can offer some value, the work that you really enjoy. Try to find it and, basically do the best in that field. Because that way you will be happy, because to compete in today's world, you have to, really excel and work very hard. And excelling and working hard will become a lot easier if you are working on topics that you're passionate about. If you're working on a topic that you don't care about, and if it is just a job to you, then, excelling at it and being able to do a lot of hard work will be very difficult, and then life is not fun at that point, right? So idea would be, find where your passion is, what is a cause that you really care about, and then, get involved in that cause and hopefully make the world a better place. And if you're enjoying the work, then you will be really good at it, and you will be able to work hard and have fun at the same time.
Okay, sir. I would again ask the participants, if you have any questions, then you are feel free to go ahead. Anyone with any questions regarding additive manufacturing and robotics, you are feel.
Sir, I have a question.
Sure,
Hello.
go ahead.
Sir, is 4D printing have a better future than 3D printing?
4D printing is going to be a niche area. 4D printing, I don't think is going to be, useful in the broad context of things. 4D printing, it will find use, but it's not very general process. So in my mind, it will be a useful process for certain class of applications.
Okay. Thank you, sir.
Okay.
Hello, sir. This is Ashish. So, sir, okay, questions are like, it's not a question. It is just like I wanted to ask that, is there any field that you are working currently and wanted to, state that problem statement to us so that we can think on it?
I mean, so whatever, topic area I discussed, those are all the topics in which currently we are working on it, and we are trying to move, make further improvement in all of those topic areas. And each of the paper that we publish, usually towards the end of the paper, we identify what the future directions are. So if you take a look at some of the papers, and if you're looking into, so if you take a look at the 2020 survey paper with robotic and additive manufacturing, we gave a long list of open problems that people need to work on. So if you can take a look at that one, that might give you some ideas.
Sure, sir. So apart from 3D printing, what are the different aspects of robotics that you have worked on?
So we worked on 7 different applications. 3D printing is just one of them. We work on robotic finishing, which is sanding, polishing, buffing type of applications. We work on composite layup, where we take pre-preg sheets, we lay them up. We work on bin picking and kitting applications. We work on basically robotic assembly. We work on machine tending, where robot go and feed the part into the machine, take the part away from the machine. We work on robotic inspection. So we work on many different applications with robots, and each one has its own sets of challenges. So
yeah, exactly. So which one was the most challenging one, like as per you?
So the most challenging problem is composite layup, because there we are manipulating compliant materials. So
okay, thank you, sir.
Any other participants? Do you have any questions? Then feel free to ask. Or we can proceed further.
Good morning, sir. Sir, my question is, what are the future prospects of mechanical engineering in collaboration with robotics?
So, I mean, mechanical engineering is a large part of robotics, right? So I think a lot of future roboticists are going to come from mechanical engineering discipline. So, mechanical engineering has played a very important role in robotics. Mechanical engineering will continue to play a very important role in robotics.
Thank you, sir.
Now I will hand it to Nasir.
Thank you. Now moving ahead to conclude this session, we have a token of appreciation for you, sir. Please accept that I am presenting.
Okay.
Yes, sir. From our side cell, we have this appreciation for you.
Okay.
Please
Thank
accept.
you. Thank you very much.
Okay. Hello.
Yeah.
Okay. So, sir, on behalf of NIT Durgapur family, I extend a really hearty vote of thanks to our eminent speaker, Professor Gupta. So, sir, thank you so much for sparing your valuable time to motivate us and to inspire us in spite of your busy schedule. Today, we had an opportunity to hear your inspiring or enlightening lecture, and this will surely going to be motivate us and encourage us in our future work. So we are grateful to you, sir. And I also convey my sincere thanks to all the participants. And with this, we like to conclude our session and have a good day. Thank you, everybody.
Thank you. Really appreciate it. And it's a pleasure. And I enjoyed interacting with the students.
Thank you, sir.
Okay. Thank you. Okay. Bye-bye.
Okay. Bye, sir.
Bye.
Thank you, sir.
Thank you very much.
Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
For getting the participation certificates, all the attendees are requested to fill the